Does anyone have their understanding check to turn in? Thank you. Thank you. Thank you, Marshall. There we go. Understanding checks. Understanding checks. No? Already have yours? Understanding checks. No? Use that rubric to identify what scores you think you earned. So don't forget, like, I will say this. I'm going to score these understanding checks. What was the point of me asking you to score it yourself? To familiarize yourself with the rubric. When I score these, I do not want you to just look and say that's a number. I want you to look and recognize that number means something for what I see as your level of evidence of understanding. Keep that in mind. And so this is to help you gain feedback and get better at knowing what I'm expecting out of you and all those different things. So please make sure you take care of that business. It is officially due today, so if you turn it in after today, it is late. Every day it's late. It's how much off?
10%.
10%. Whoops, sorry. Thank you, Naisha. My bad, Desiree. All right. With that being said, I completely intended to grade the homework assignments that some of you had turned in late. I have not finished. I'm about halfway there. I will get it done today. Just had to work on other things yesterday. If you didn't notice, and this is why I didn't get it done, I sent out everybody's Google Sheets with the active collaboration scores. So look in your email, either your TCSS email or other email. I made sure that I sent it to everybody's TCSS email, but also if you gave me an email and if that email worked, I sent it to that other email as well, so that you can keep up with your active collaboration scores, okay? And so that's to help you keep track of what am I seeing. The higher your active collaboration, what's going to happen? What's going to happen? The more you're going to learn. Right? The higher your active collaboration, the more you talk things out, the more you're going to learn. That's the point. And so if I only see you at a 2 or a 3, you're not going to learn as much as someone at a 4, 4.5, or a 5. And it's not about how correct you are, it's about you engaging and trying the problems and trying to make sense of the things I've given you. So we're going to talk about that more moving forward, but let's look at this bell ringer question. All right. And by the way, I have been checking the responses y'all have for if there's things going on, and I'm going to try to check in with those of y'all who have said you have things going on, but understand, like, that is a time for you to say whatever you need to, and if you need to talk with me, that's a good way to say, hey, Mr. Kenny, I need to talk about blank, okay? I do care about you as a person, not just you as a math student, so that's why I have that question in there. But let's look at these problems. We need to pay attention and talk about this. A lot of us are starting to see a pattern here. The most common responses, 7, 11 of us basically have the same answer. And this person probably meant something similar, but they forgot a plus sign. We have 2p plus 4r equals 16. Where is that coming from? 2 paintbrushes, so why is that 2p? Okay. Say it again. Repeated addition. Like, what's unknown here? How much each paintbrush costs, right? So we can see that as each paintbrush is p, so p plus p. I'm repeatedly adding the cost of those paintbrushes, and that's what I want us to notice. Like, anytime you write a variable with a coefficient, there's understood what? Multiplication. And if there's multiplication, that what you're indicating is that there's repeated what, Jacoby? Repeated addition, guys. That's what we want to recognize. When we talk about the masking tape, right, the rolls, which is why some people use R there, and you could have used any variable. I'm good with whatever variable you use as long as it made sense. Why is it 4R? 4 rolls of tape, so why does that become 4R? Yes, but if we write 4R, what detail do you need to go back to every single time? Okay, we're talking about repeated addition, right? Like, that's what I'm looking for, because you have to think through that detail. What's being repeatedly added in that 4R?
4.
Well, not 4, we're not repeatedly adding 4, we're repeatedly adding R, the cost of each roll, right? I have the cost of each roll, and each roll, or how many rolls do I have? 4, that's why it's 4R. And so we have to pay attention to which one's being repeatedly added. What's being repeatedly added is the unknown cost of that roll of tape. And now I know that that sum is $16. Questions about that bell ringer before we continue? Are we getting a little bit more comfortable with identifying that equation? Please understand, guys, bell ringers are supposed to be quick. Sometimes they're going to be a little bit harder first off, but we should get more comfortable as we practice them over and over again. And it's supposed to be a learning opportunity. This isn't an assessment in the sense that I'm giving you a grade for this, but I need you to engage and talk about these things so that you can learn better. Does anyone recognize what type of equation we have there? We want to start to recognize that standard form. And I do want to point this out. I talked about yesterday that we always talk about mathematics is the study of what? Patterns and relationships, right? And we'll see it again later in a second. But with that, we're going to do what 3 things? First, we're going to notice. I want to pause there. Do you have to have really technical mathematical language to notice something? No. But what comes after noticing? You need to describe things. You don't need super technical mathematical language to describe, but is it easier to describe things if you know what the term is in math? Yes. But then after we describe, we're going to generalize, okay? And when you generalize, you do need that mathematical vocabulary. So we're going to start with things that you don't need super technical math vocab for, but then we're going to build to where you need that mathematical vocab, so pay attention to that. A key thing here that we need to know is, hey, that's standard form of a linear equation. We need to know what that means. So learn your vocabulary. I'm going to embed vocab throughout this entire thing, right? I think Jamarcus was the one who said, like, are we going to have vocab tests? And we're not. But I'm going to use that vocabulary in assessments. So if you don't know that vocabulary, it's going to be rough. You got to know your vocab. Questions, comments, concerns before we continue with the rest of today's lesson? No? Got one no? Everybody else okay? Can I get a quick show of thumbs up? Just right here if we're feeling okay. Down if we're not. Sideways if it's eh. I have some people who still aren't giving me a thumbs. Phoebe, you awake over there? Where's your thumb? Mickey? Okay. Where's your thumb? Where's it at? Thank you. Alright guys. It's just a quick feedback. I need to know where we are. Okay. Really quickly, please remember this because I see a lot of us have the task Dream Job Salary out on our desk. But when we work through the Dream Job Salary, this is not just a completely new assignment that we have never done anything with before, or we haven't dealt with concepts before. What should we have out to help us tackle a task like this? Notes. Everything in math builds, guys. Everything in math builds. So we need to have quick access to our notes. As we're working, we want quick access to our notes. Another detail is this. I'll go ahead and tell you, when you turn assignments in on time, I'm usually pretty good about getting those assignments graded and back to you. If things are late, okay, I will get to them. It just takes me a little bit more time. Sorry, I'm just trying to CD on so we can use it in a minute. And I need you to hear me very clearly because I became very frustrated with a student in my third block yesterday because she came at me about her grade. Well, she turned in her assignments late. I'm going to get to them. But don't ever come at me about your grades when you did not do what you needed to do, okay? I'll work with you to help you learn better. And if you learn better, what's going to happen with your grade? It'll go up, okay? I'm going to bust my butt to help you have the best learning experience possible if you are actively collaborating and working in class, okay? I'm going to do everything I can to help you grow and learn. But do not come at me about your grades when you haven't always done what you're supposed to do. Okay? I want the best for you. I'm going to fight for your best. But you got to learn in my class at the end of the day. Getting ready for class, we did pretty well today. Please make sure you get seated, you get your stuff up there before the bell rings. Missing days of school. I need to do better about updating Schoology, I'll agree there, and I'm going to try to start getting that up daily. But if you miss a day of school, you need to stay on top of your work. How can you do that? YouTube. So, and Grace, you used it, right? You searched my name, came up pretty quick. It's dated. I haven't updated the times for the last 2 days, but for most of the videos, I have literal breakdown of the times where things are covered. Okay. If you miss a day of school and you come back, have we done learning while you were gone? Yes, of course. My job is to teach and try to help you learn as much as possible. If you miss school, you cannot sit at home and just say, well, that's it. I get if we're having a really rough day, maybe we don't watch the video that day, but you need to take the time at some point to watch the videos, come in, and be ready for class. Because if you come in, you will have missed things. So please be aware of that. I want you to be successful, but you also need to take responsibility for what you're doing. Today we're going to work on the dream job salary task. This traditionally takes about 30 to 45 minutes, so we'll see how that goes. And then we're going to get into something called the gold rush task. Notice we're moving away from just solving problems. We're starting to study what concept, what word shows up in both of those things. Functions. We're going to study functions. More than anywhere else we've already been, functions are where patterns and relationships will show up over and over and over again. You need to notice them, and then we're going to describe them, and out of describing them, we're going to generalize. Pay attention to that. We already talked about it. Math is the study of patterns and relationships, so we're going to notice, describe, and generalize those patterns and relationships. And so here's our objectives. You need to pay attention to this, because this is the foundation for this task. You need to be able to tell the difference between the rates of change for linear and exponential functions. We started on this yesterday. There were very clear differences in those types of functions. And so most of us noticed it already. We started to describe them. Continue with that. We're going to look at how linear and exponential functions appear in tables, graphs, and equations. Notice this is why we did the to use or not to use algebra, because we need to be able to look at all three representations. A linear function is linear, and it looks different in every representation than an exponential does. So we got to know what those differences are. And then finally, we're going to work towards writing equations. You've written equations with linear functions in the past. In fact, this is a type of linear equation, standard form. This is not the type you would want to use here, and I'll explain why later, but we're going to work on writing equations for linear and exponential, using what we already know. So remember, Kiowa has a 30-day contract, so can you just look at 7 days and make a decision about which contract he should go with? Nah, you got to get all the way to day 30. And I believe one group over here got all the way to day 30 using a table. Which group was that? Y'all did? That was a pain in the butt doing all 30 days, wasn't it? No, it was easy? Once you found the pattern? No? It was just easy? Man, I will say this, I think it's an easy entry point. I just don't want to have to write out 30 days. That's my thing. So if we could notice a pattern or relationship, that might be helpful, right? If we could write an equation, I'll point out, can you just substitute the number 30 into the equation if we could figure out what the equation is? Could that have been quicker? Yeah. What else could we have created? Starts with a G. Graphs. Once you have that equation, it's pretty easy to create the graph. So consider those things and keep that in mind. Do not forget, right? Everyone's usually pretty good with option 1, $60,000 a day. But in option 2, he gets a signing bonus of a penny. So even if he has worked 0 days, how much money does he have? 1 penny, or $0.01, right? And if he works 1 day, he gets another penny, so he has a total of 2 pennies, or $0.02. And so we want to pay attention to that relationship and look at what's happening there. So we should be figuring out which payment option he should take, supporting your decision using at least 2 representations for each option. So please notice, is it enough to just make a table? No. We also need to make what? Either a graph or an equation. Now, you can make a graph by hand based on the table, but I will point out number 2 says create an equation for each payment plan, so I would try to work towards that at this point. If you finish number 2 before we come back for our whole class discussion, you can move to the backside for number 3, but I'm going to try to get to number 2 pretty quickly. Any questions about the context of this problem and what we're trying to do? Okay? There's only one group, I believe, that hasn't used the TV yet. Which group is that? Nobody wants to volunteer because they haven't used the TV? Cool. In that case, 6, it's been a while since y'all have gotten to use the TV. You were the first ones who used it, so you get to use the TV today. Let's go, who used chalkboard yesterday? 7 and 5, so let's go 1 and 4 chalkboard. And then 7, you'll use this whiteboard. 2 and 3 are the only ones I haven't assigned yet. Let's work together and we'll use this this whiteboard. Everybody know where they're moving. Alright, let's get up, let's get to work, let's find out which option Kilo should take. To that group that when we look at this table, we should start to notice, well, if it's 60,000 every single day, how much, what are we repeatedly doing? Adding. So over 5 days, I could do 60,000 times what? 5. Now I can go by 5 days. And every 5 days is adding how much? Well, that speed things up a whole lot. Pay attention to your patterns and figure out what's going on. Hey, multiple or repeated addition is shown through multiplication. So now, over these 5 days, I'm going to add another 300,000. Over these 5 days, I'm going to add another 300,000. I would write that all the way out. So it's 1,200,000. And over the next 5 days, I'm going to add how much? 300,000. So that's 1,500,000. And then on day 30, it's 1,800,000. Repeated addition, that pattern can make our lives 1,000 times easier. Pay attention so that we don't have to go by ones. And then from there, we need to pay attention to option 2. What's the pattern in option 2? Times 2 every single day? Is it doubling? Yeah. So we're multiplying by 2 every single day. So over 5 days, what's happening? Multiplying by how much? So if I do times 2, times 2, times 2, times 2, times 2, pick up a calculator. Or just do it. What's 2 times 2? 4 times 2? 8 times 2? 16 times 2? 32. So over those 5 days, we multiplied by 32. So over the next 5 days, what are we going to do? Multiply by 32. Pick up a calculator. 0.32 times 32. What do you get? Pick up the calculator. 0.32 times 32. Say again. 10.24. That group over there, we need to pay attention. Little off on that table up in pink, so we need to be careful and pay attention. I was wondering if that happened. So we got to be careful with our multiplying by 2. We're going to get similar answers, but we want to be accurate. What's going to happen over the next 5 days? What about 32? We got to show that multiplication by 32. So day 15, how much has Kilo made? How much? 10.24 times 32. 327.68. And I'll start to point out, could I just do times 32 times 32 to go by 10 days? Sure, right? You can start to notice these patterns. But multiply by 32 again, what do I get? Somewhere in the thousands, I think. Maybe 10,000? 10,000? 10,000 how much?
485.80.
Multiply by 32 again. Notice, this is not necessarily easier, but it is quicker. And once we get comfortable with it, it becomes easier.
335,544.
335,000.
544.
544. That's fine there. Okay, so I want to point out, like, through day, what is that, 25? Kilo's definitely not coming out ahead. But After that, I multiply by 32 one more time, and how much is Kilo going to make in option 2 after 30 days? I believe it's 10 million, 377,000, 408.
I got 737,000.
Okay. 737,000,
Uh-huh.
408.
Okay.
I probably misheard it. Okay? Thank you. So please notice, first off, if we notice patterns and relationships, does it speed things up? Yes. Notice those patterns and relationships, especially because that pattern is going to define a different function. I would note that one function has repeated addition. One function has repeated multiplication. I would note that.
Yes, sir.
One function has repeated addition. The other function has repeated multiplication. You can write that down either under number 1 or on the back side where it says whole class notes or something like that, I think. Okay? We've been over this pretty extensively. If we're repeatedly adding, what should we immediately think about? Repeated addition becomes multiplication, right? That repeated addition, we're going to show through multiplication. But we just pointed out that we now have repeated multiplication. How are we going to show repeated multiplication? Say again? Kind of, but here's the thing. Am I going to write, if I have 2 times 2 times 2 times 2, am I going to do 2 squared? Is that the same thing? Say again? 2 to the 4th. So what are you talking about there when you say 2 squared and 2 to the 4th? We're talking about an exponent, right? Note this, positive exponents show repeated what? Positive exponents are going to show repeated what? Multiplication. Positive exponents are going to show that repeated multiplication. And we want to notice that. Because this equation is going to be different. Because it's a different rate of change, it's a different function. And so I'm going to have you go back to your small groups. Actually, I'll just have you work at your desk for a minute. But I want to point this out. When I look at option 1, how much money does Kilo start making in option 1?
6,000 a day.
He does make 60,000 a day, but if we're talking about day 0, how much has he made? $0. So if I'm looking at option 1, Kilo starts out with $0. If he works for 1 day, how much is he making? 60,000, right? If he works another day, how much more does he make?
Another 60.
Another 60,000, right? So he has 2 60,000s. Well, that should say just, sorry. That's day 0, so plus nothing. Then 1 times 60,000. And then if he works the second day, he's getting another 60,000, right? But it's times how much? 2. And so I want you to think about this and figure out how can we write an equation based off this one. This one's going to be the easier equation to write, but I'm pointing this out because when I look at option 2, how much money does he start with in option 2? 1 cent. So I'm going to write that as 0.01. And to get day 1, I'm going to take that 0.01 and I'm going to do what to it? Multiply it by 2. How many 2's? Just 1, 2? 0.01. I'm going to multiply it by, to get to day 2, I'm going to multiply it by 2 2's, right? So I'm going to write that as 2 to the second. Because that exponent is going to show my repeated multiplication. So what I want you to do is I want you to take just a couple minutes, try to write an equation for both option 1 and option 2. This should go under number 2 on your page, right? Try to write an equation for option 1 and option 2. Think about that information that we have up on the board. Bless you. By the way, guys, this doesn't have to be silent. Actively collaborate, talk with each other to figure out an answer for number 2. Generate some ideas. So 0. Come on, guys, y'all know how to do that first one. He's repeatedly adding 60,000. What are we going to do? I want an equation. Right, I want a function. Well, but hold on, pause. You're giving up on that. Oh, hold on. But my point is, 0 plus 60,000, it's going to end at 30 days, but I want something that works for any number of days. So if it's 1 day, it's 60,000 times 1. If it's 5 days, it's 60,000 times 5. If it's 10 days, it's 60,000 times. Something's changing there. It's varying. We need something to represent
Like
that.
the equation, I think it'll be 0.01 times 2.
At least one of us has an expression. Let's talk with each other, see if it makes sense, what we think for option 1.
What is this?
So one thing I want to point out, I'm going to recommend here is I want an equation that works for any number of days. Not just day 30, I want something that works for any number of days.
You multiply on each day, it should be the same.
So like if we're looking at day 5, we're multiplying by 2 to the 5th. Could we put a variable?
So you want to have a certain.
I don't think I'm gonna put a day on there.
Can we do that? With variables represent our number of days, because the days can change. Think about that with option 1 as well. Phoebe, Mickey, are we good with that idea? Are we actively collaborating? You sound so angry. What's wrong? That doesn't answer what's wrong. So you want to talk outside when we go back to our whole the boards? Yes, sir.
Alright, so we're talking about how like 0.01 times 2 with the 2 as the exponent. And I was thinking, so on option 1 we did y equals 60,000 would be made per day times days, because we don't mark for each day we go through.
Right.
So on option 2 we did just be y equals 0.01 or times 2 with an exponent for each day.
Could that make sense? We didn't talk about it as a whole class, but what you're saying there is we're multiplying by 2 for each day, and we don't know how many days it's going to be because it can change.
Right, like the exponent on the 2,
Yeah.
as the day goes up, will it change too?
If we look at day 3, how many times are we multiplying by 2? 3 times, right? If I'm looking at day 17, how many times have I multiplied by 2? Right? Something's changing there. Thank you. Thank you. Thank you. Okay. Guys, those who are talking the most are figuring things out. And I hear some good ideas being shared, but if you're stuck on this, talk about this with your group to help each other figure it out. I cannot force it, but I am telling you, the people who talk about these ideas are going to learn more than anybody else. So let's look at option 1, right? Can somebody give me an equation for option 1?
0 plus 60,000 times 8.
Okay, so I'm going to do this really quickly. So what did you use for your independent variable? 0 plus what?
60,000.
0 plus 60,000. Then you said times something? Times A? Why A? Just out of curiosity.
You can plug it on any day for that.
So why would you use A?
You don't have a certain number.
Okay, so you're talking about the variable. I'm talking about the other side of it. Why did you choose A as your variable?
First alphabet.
Okay, I mean that's fine.
I think we got 2 different.
I got you. Does anyone know what might be a really good variable if we're talking about days though? I would have probably done D or X or N or something like that. Those are common ones. Can you use A, guys? 100%, right? So David, I'm not saying you're wrong. I'm just saying in the context, I might use the letter D. Does that make sense? Can anyone explain to me where David got this? Where are we getting, and I will say we don't need the 0, but can anyone explain to me, David started, but where did 0 plus 60,000 D come from?
Yeah, how much you make a day?
That's how much he makes a day. I need a little bit more to it.
That's how much you, that's how much the repeated addition is.
So there's repeated addition. Where do we see that repeated addition? Not in the variable. What shows the repeated addition? Just the multiplication. We're going to pause on that, right? Remember, the multiplication is what's showing repeated addition, and what's being repeatedly added? The 60,000. So, repeated addition. That's repeated addition by 60,000. I'm going to put a K for simplicity, but by 60,000 each day. Okay? That 60,000 times is what's showing me my repeated addition by 60,000 every day. Multiplication is repeated addition. So why is there a D there?
For the days.
What about the days? They can
Change.
I want to point this out, and this is why I wrote it this way. So pause if you're writing that down. Look over here. I know if you're in group 1 it's hard to see, but look at this equation. You see how that 60,000 shows up in each of these? But then we have 1 day here. We have 2 days here. Could I have also even done 60,000 times 0 for 0 days? Would that have given me the same answer? If I look at day 17, it'd be 60,000 times what? 17 to match the number of days. And so when we look at this, right? The D days is how many times? 60,000 is added. Please notice I'm breaking down this equation because if we understand where this equation comes from, we can use it in new situations. Every equation that has repeated addition can be written in this form. Every equation that has that repeated addition can be written in this form. And this is also going to explain the second equation that we need to do. And I would probably make this note here, but that can change. Which that explains why we need a what? A variable. It is important to notice that the number of times I add 60,000 can change. That's why we have a variable there. Every part of this equation makes sense. It's not random. Now, that 0 is a little weird. Why do we need the 0? You don't need it. But why might it be a good idea to include that 0? What is that 0 representing? How much you started with on day what? 0. If we're graphing this, does anyone know what that 0 would represent? It would be the origin in a special case like this, not the x, the y intercept. Day 0, he has $0. That's my y-intercept. That's my y-intercept. 0 days, $0. The y-intercept is a great starting point for equations. And then, final detail here, f of, this is not f times, oh, we're still writing, sorry. Oh, we're done. So this is known as f of, for function. Does anyone know what variable I need to put inside of this function? It could be x, but based on this problem, it's going to be d. What goes on the inside is my input variable. The outside is my output variable. The way that this works and is useful is if I say f of 7, what did that 7 take the place of? D. So in the right-hand side of the equation, I get 0 plus 60,000 times what? We're going to get more experience with this. This is just an introduction to it. But that means f of 7, if you work it out, is 420,000. What that's saying is, on day 7, he had made how much money? 420,000. This is the point and the beauty of function notation, is that I can see both my, what is this called again? So it's going inside the equation, so it's my input, and then this is my output. Function notation is going to show me my input and my output. So now we have an equation written. We haven't talked about what type of function it is yet. We'll get there soon. But we have an equation. I talked about that function notation a little bit. What questions do you have about this information? Going once? Going twice? Sold. All right. So let's look at option 2. Did anybody come up with an equation? I'm going to start off with f of d again, right? Just function notation. Actually, technically, this would need to be h of d or something else. Please note I changed this because f of d only is for which option? Option 1. Putting a different letter out here, all that means is it's a different function. So I can't use f of d again, but is d still my input? Yes. H of d indicates it's a different function. So did someone come up with an equation here? By someone. I know at least one person did. Say again? P times 2? P times 2? Like that is what you wrote? Okay. Anybody want, can you explain that to us, I guess? Okay. It's okay. I'm just asking for options and ideas. David, are you raising your hand or no?
0.01 times 2 greater than equal.
So h of d equals 0.01 times 2 raised to the d. Marshall, I think you had a similar equation to this, right? Where did you get this from? Look over at the TV. What did we start with every time in option 2?
0.01.
Right. How much money did Kilowatt start with in option 2? $0.01 or 1 penny, right? So what are we going to start with? 0.01. And then when I look over there, repeatedly, what are we doing? Multiplying by 2. Every expression over there has a times 2. But what's changing? It's times 2 and then it's raised to the first for 1 day. Raised to the second for 2 days. If we're looking at day 17, we're going to do times 2 raised to the 17th. So this thing is varying, it's changing, so we need an exponent, but the exponent needs to be a variable. It's changing based on the number of days. And also, it's not because it's changing that we need an exponent. Why do we need an exponent? Because it's repeated multiplication. Focus on that detail. We need an exponent. Because there is repeated what? Say it louder. Multiplication. So why did we use D as that for that exponent? Why did we put a variable there?
Couldn't put just a certain day.
We couldn't put just a certain day, yes. But remember, if we're using a variable, what is that always indicating? That things are changing. Is the number of times we multiply by 2 staying the same, or is it changing? It's changing. So I need to use a variable, right? We use D because the times, the number of times we multiply by 2, or times multiplying by 2 is changing. We're going to use variables when things in that expression or in that equation are changing. And that exponent. Right? Needs to be a variable. We're almost done breaking this down. There's only one last thing that we're going to do. If you're already done taking notes, pick up a calculator and create a graphs page. We're going to get there in just a second. Okay, so once you have a graphs page, I'm going to put one more note up here, and then we're going to go to the graph. So put the calculator down after you create that graphs page. Really quickly, I want to point this out. Why did we use a 0 right here? That was my what? That was my y-intercept, right? It's when our days was 0. Over here, what is that 0.01? Right, but on what day? Day 0, that's my y-intercept. Notice both of these equations are starting with what key point?
They're starting though.
Day 0, which is our y-intercept. That equation starts with the y-intercept. So, starting point of y-intercept. You don't always have to use the y-intercept, but it is the easiest. Starting point of the y-intercept. And what's that times 2? That's my repeated multiplication. So notice that's my rate of change. That's my repeated multiplication, or my rate of change. Now we're about to look at these two graphically. One of these functions is what type? Think about your objectives. What were the two types of functions we're trying to look at right now? It starts with an L and an E. Linear and exponential. Just give me a prediction. So get involved in the conversation. Which of these do you think might be an exponential function? Which one? Why do you think second one? Not trying to trick you. Huh? Just guess? Anybody have a reason why the second one might be exponential?
Exponential sounds like exponent.
Exponential sounds like exponent. Yeah, what's our exponent in option 2? Well, in general, we would call that a variable. That's what I want us to notice. We have a variable in the exponent. Could that be significant? Very much so. Variable in the exponent may be exponential, which would mean option 1 would be what type of function? Linear. By the way, what do y'all already know about linear functions? This is something we should hopefully pull with us from Algebra 1 and even middle school.
Lines.
Huh?
Lines.
Lines, yes, it's linear, it's a line.
Intersect.
But what do you know about the rate of change for a linear? What I pretty consistently hear from students year after year after year is that a linear function has a constant rate of change. Do we remember that? But I want to point this out, it's more than just a constant rate of change. Linear has a constant what? What is constantly happening in option 1? It's constantly adding. Whereas in option 2, is it constantly doing the same thing? You sure about that? What does constant mean? It's just the same thing over and over and over again, right? Option 2, is it constantly doing something? What's it constantly doing? Multiplying by 2. So it's not enough to say with a linear that it's constant. We need to figure out which type of constant it is. So pick up the calculator. Let's graph these two functions. I know it must be really tough to pick up calculators. Alright, so add that graph. Now we'll point out, do we have function notation so we can use f of x equals? We have function notation so we can use f of x equals. What's the first one we have? Times what? Remember, we can't put d in the calculator. We have to put x. Enter. Okay, so we at least see something there. That looks like a vertical line. But remember, we're repeatedly adding what in that case? You guys notice the equation is still on the board in blue. Right? It's there on the board. We're repeatedly adding 60,000. That only goes up to like a 7 in the y, so we might need to change our window. That's something we would want to notice, right? And so I'm going to go back to menu. I still need to create the second function. So after I hit menu, where do I go? Graph entry. / edit. Tevin. Come on, put the equation in. Hit menu. Go to graph entry / edit. Then we can do function. If we don't have function, you can always use relation, but we're using function now. What is the second function we have for option 2? 0.01 times 2 raised to the x. If you don't know where an exponent button is, if you look at the control button and look 2 down, you'll see a little caret there. That little caret is how you do a raised to. Yeah, that's the name of that arrow symbol. It's called a caret.
Oh, you should have said arrows.
It's called a caret. Well, weirdly enough, it comes from English, and it's called a caret. It's a symbol that if you missed a word, you can put a little caret there, and it points up to show that there's a word above the sentence that you were supposed to add in. It's not C-A-R-R-O-T, I believe it's K-A-R-O-T maybe? I'd have to check the spelling, but it's called a caret. All right, hit enter. So we can at least see them right now, correct? Yeah. So I need to change, and I will say right away we see some evidence. Is that red function a line? No, so it's probably not what? It's probably not linear. Okay, so let's change our window settings. What are we going to do to change our window settings? Menu. For window / zoom. Now let's talk about window settings. Let's think through what would be intelligent, okay? X is referring to what variable? Our what? Our days, right? What would probably be a minimum number of days that we'd want to see? Minimum. The lowest number of days. We want to see 0, right? I'd probably go a little to the left of 0, so maybe a -2 or a -3, right? So that I can easily see that 0. Again, x is our days. What number of days do we definitely want to see? 30. So maybe a little bit to that right, so 35 or so. Notice I'm not doing anything crazy. I'm just thinking about the variable in the context. I'm talking about days, and I want to see 30 days. So I'm going a little bit outside of 0 and 30. I would just leave my scale as auto. You can play around with that in the future, but we don't need it right now. Y is referring to the amount of what? What was the output? Based on the number of days, we were looking at his amount of money, right? So we got to pay attention. X was days, output was money. So what is the lowest amount of money that we definitely want to see? 0, right? 0 days, we had 0 money in option 1. So I go a little bit below that, maybe, actually you can probably leave it where it is. What Y value should we look at? Huh?
Already X'd it out.
What do you mean? Oh, then just put -5 or whatever. That's fine. What can I put for the max now? Since we've already made the table, we know option 2 ends at how much? 10 million, so we need to go a little bit more than that. Maybe
11.
you can do 11. I was going to do 12 because it is pretty close to 11 million already. So 1, 2, 1, 2, 3, 1, 2, 3. Right, so you need 6 zeros in there to get 12 million. Make that scale automatic. After you have all that, what are you going to hit? Enter. Does anybody need me to wait on hitting enter? The vast majority of this contract, which option was better? The vast majority of the contract? You see how option 1, the blue line is above that red curve? Right? But all of a sudden, at some point, because it was doubling, option 2 caught up and passed it very quickly. Notice in option 1, kilowatt ended with 1,800,000. Option 2 ended with 10 million plus, right? That's important. So we can very clearly see which of these functions is linear. The blue one, 0 plus 60,000x. Because repeated addition creates what type of function? Linear. Constant addition creates a linear. Constant multiplication is creating this red curve called an exponential. I'm going to write that in a second for you to get that in your notes, but those are fundamental things. What defines a linear function is a constant additive rate of change. Regardless of the equation, of if it's in an equation, a graph, or a table, a linear function always has a constant additive rate of change, every single time. Regardless of whether it's in an equation, a graph, or a table, an exponential function has constant what? Linear was constant addition. Say again. Constant multiplication is defining that exponential. Which is why it's named exponential, because an exponent shows repeated what? Multiplication. Now, I'm just going to do this quickly because we've been doing this a little bit. How could I use this graph to find exactly when option 2 caught up with option 1? I'm going to find that point of intersection. Go through it just to get a little bit of practice with this skill. Go to menu, analyze that graph, and intersection, right? So menu, we're trying to analyze that graph and intersection. Now it's in scientific notation, but we can very clearly see what day it was. You only have one function. You have to put the second function in. Hold on 1 second. You need option 1 still. So 60,000 next. Yes. Now you can do intersection. Say again. You got it? Oh yeah, you can click on it. So, what day did option 1 or option 2 catch up with option 1? Day 27, day 28, somewhere in there, right? So I just want you to notice we can still use graphs to solve the problem. Hey, if I ask when does option 2 catch up with option 1? Day 27. So if Keelo's contract was less than 27 days, what option should he have gone with? He should have gone with option 1, right? If it's after day 27, which option should he go with? Man, option 2 is way ahead after day 27. Repeated multiplication is going to catch up with repeated addition at some point. All right. Final notes that we need to take based on this information. And you can put it with this right here or not, it's your choice. But this is y equals, you can do it as a plus bx, y-intercept, right? Anyone remember what the constant additive rate of change of a line is also called? Starts with an S, SL, slope. That constant additive rate of change of a line is called a slope. There's my slope. We're going to go into more detailed practicing with this later, but we want to notice we have a y-intercept and we have a slope. That's how we wrote this equation, a plus bx. What is the normal slope-intercept form that you've done? It's written backwards, but is that telling the same story? Okay? So I would want to point out, it doesn't matter how it's written, the slope is a constant additive rate of change, and what shows repeated addition? What shows repeated addition? Multiplication. You see this multiplication right there? You see this multiplication right there? It's this multiplication that's telling me what my rate of change is. It's that multiplication that's telling me about the repeated addition. Whereas this A and this B, how many times are they showing up in the equation? Once, that's my y-intercept. That multiplication is telling me about my repeated addition. You can write the linear equation either way. I personally like this one because it's going to help us with the exponential equation. So if we're thinking about that, write y-intercept and my constant additive rate of change, what is the equation for an exponential? What am I going to use for the y-intercept? What symbol or letter? A. And an exponential, what's repeatedly happening? Look at how we set it up. It's multiplying, right? Notice how this was my rate of change. What's the rate of change, that symbol that we're going to use for an exponential? B still. We're still using B for rate of change. But it's going to be times B raised to the, what's going to show that repeated multiplication? What operation? An exponent. But we're changing how many times we're multiplying, so that exponent needs to be an x, a variable, right? We use x for those inputs. So still the y-intercept. And this is my constant multiplicative rate of change. And I know that language is unfamiliar for most of us probably, but that's what it's called, a constant multiplicative rate of change, called a constant factor. You will hear me ask, okay, so what is your constant factor? What do we do with factors? No idea? What are the factors of 6? What are 2 factors of 6?
2 and 3.
2 and 3. Because what do you do with those factors? You multiply them, right? What do you do with factors? Multiply them. What's happening in an exponential function? It's repeated multiplication. That's why it's called a constant factor. It's constantly what we're multiplying by. Everything in math has a reason. It all connects. We need to find those connections. So it does not matter what representation, what is defining a linear function?
Constant addition, rate of
So, it doesn't, representation does not matter. A linear function always has this rate of change. That is a key detail. That is something that you should star, you should highlight. It does not matter what representation you're looking at. If it's a table, if it's an equation, if it's a graph, that linear function will have a additive rate of change. Constant additive rate of change. So if you see a constant additive rate of change, you know the type of function is linear. If it has a constant additive rate of change, you know that it's linear. Say again. So if you see a constant multiplicative rate of change, what are you thinking about? Exponential. The representation does not matter. An exponential function has a constant multiplicative rate of change. Are we familiar with ROC as rate of change?
Yes.
Okay. Just be aware, ROC, rate of change, right? So it does not matter the representation. An exponential function has a constant multiplicative rate of change. What are your final questions about linear and exponential functions? Final questions about linear and exponential functions. You need to hold on to this sheet for studying purposes. If I can grab your attention, I want to point this out. Did you need me to tell you about the pattern of repeated addition or repeated multiplication? You can notice that on your own. That's my point. You can notice that pattern on your own. And then I asked you questions to help you describe it. And then at the end of describing it, I tied all these things together so that we can generalize. That's what mathematicians do. They notice, they describe, and they generalize patterns and relationships. That's what we need to continue to do. Within this next task, I'm going to show you how to use tables on the calculators as well. We are going to skip number 3. That was just an extra if we got there. But here is the next task that we're looking at. So we talked about what 2 types of functions? Linear and exponential. And guys, don't forget, this is just an intro. We're going to get practice with this stuff tomorrow and or Monday. By the way, Friday, bring your tablet or your iPad with you because we have to do iReady testing. So Friday, make sure you have your iPad with you and it's charged because we have to do iReady testing. Not until next Tuesday or Thursday. But I'll remind you that then. Alright, so right here, guys, right here. We need to learn what rate of change defines a quadratic function right now, and we need to look at how quadratic functions appear in tables, graphs, and algebraic representations. Alright? And then we're going to start writing quadratic equations, so that's not going to be the focus. Here's what we're looking at with gold rush, okay? In the 19th century, many prospectors traveled across North America searching for gold. That's true. And here's a scenario to help us understand quadratic functions better. A man named Dan Jackson owned some land where gold had been found, and so instead of digging for the gold himself, he rented plots of land, because that way he doesn't have to do the work, and he still gets paid no matter whether gold is found or not. It's pretty ingenious. But Dan gave each prospector 4 wooden stakes and a rope measuring exactly 100 meters. So what shape can the prospectors create? A rectangle. They can create rectangles. That's the point. Now, I will point this out. Is a square a type of rectangle? All that is required for a rectangle is that the opposite sides be congruent, right? So opposite sides are congruent, and the angles are 90 degrees. A square is just a special type of that. All of the sides are congruent, and the angles are 90 degrees. Okay? I bring that up because there's always a debate from students. I always hear debates from students of whether a square is a rectangle or not. It is. Just be aware of this. This problem is not just a matter of finding what are the best dimensions, because if you're a prospector, Jamarcus, Jose, if you're a prospector, why would you want the biggest area? You have the best chance of finding gold, right? And so it's not just about finding the best area, it's about learning about quadratic functions, so you need to create mathematical representations for this. Now I do want to point this out. If we are putting stakes up and we're putting rope out, could I have, let's say, 20 meters here, 80 meters here, 80 and 20? If I have 100 meters of rope, could I do this? Why not? It has to add up to 100. If I leave this as 20, what would these have to be? Not 60. 40. Not 40. 30. If I do 30 and 30, notice what is 20 plus 30? 50. And if that's 50, then this is 50, and I have 100. How would I find the area for this rectangle? Multiply 30 base times height. And what's 30 times 20? 600. Okay. Now, students get tripped up on this every year, but I want you to pay attention. Could I have a rectangle that looks like this? That's really long. And that's 1 meter here. How long would this need to be? How many? 49. Because remember, and so Ethan, you made the common mistake most students make of 98, but then that'd be 98 here. Notice 49 plus 1 is what? 50. So if this is 50, this also is 50 to get 100 meters. And what is 49 times 1? 49 meters squared. They both have 100 meters as the distance around, correct? Do they have the same amount of area? No. 600 square meters, you're going to have a higher chance of finding gold than 49 square meters. We have just a couple minutes left, but draw out some rectangles and go ahead and try to think of some dimensions. We'll create mathematical representations tomorrow. Okay? So draw out some rectangles. Talk about it with your group. We should not be packed up yet because we still have over 2 minutes, and so we're working on this.
That's not how that works.
Hold on 1 second. What's up? Maybe, but remember you're going to have to prove it, and we're trying to explore quadratic functions, so we need lots of different examples, and we need to create mathematical representations to find out about these quadratic functions, right? So notice it has completely justified the dimensions. So you're thinking this, but you need to test out other options. And so you need to develop thorough and clear evidence that supports your answer, and you need to explain how the evidence supports your answer. It has to be a rectangle. Say again? Well, you're gonna work together to try to find the best area, so we can bring them together at the end, right? So you can have different ones to start with.
Some rectangles, bro. He said draw rectangles, so I drew rectangles.
All right, at this point, we do have 30 seconds. We should have at least 1 or 2 rectangles drawn. You have no new homework right now,
Oh, but wait till the week.
but some of us still need to complete the old homework. Notice we've gone days without new homework, so I do not want to hear complaints when I assign homework soon. Yes? Okay, she is on the way. I'm assuming y'all. Please put my calculators up before you leave. By the way, I feel like there's been some good learning today, but what are all of you?
Capable.
Capable of what? More.
Cam, be quiet right now.
And be able to be alone.